Series 2 covered real-time incident response, the 10-minute workflow from synthetic alert to root cause. This video covers the slower, more important process: what happens after the incident is resolved, when the team reconstructs what happened and why. A postmortem written from memory is subject to recency bias, attribution errors, and gaps in recall. A postmortem built from multi-source telemetry is a factual reconstruction and a much better foundation for preventing the next outage. Timeline reconstruction is the first step in any data-driven postmortem. Starting from the first alert and working backward, each source contributes. In this incident, network flow data shows a traffic shift to the backup link at T-3 minutes. SNMP interface errors on the upstream router began 3 seconds earlier. The synthetic alert fired at time 0, 3 minutes after the root cause. The Kubernetes autoscaler responded at T+45 seconds, creating a pod restart cascade that compounded the latency. That reconstruction took 15 minutes with unified data. It would have taken hours across separate tools and manually aligned logs. By digging deeper into the telemetry, we see the exact moment the primary circuit degraded, forcing the BGP session to flap. The flow data confirms that while the traffic stayed within the network, the backup path wasn't provisioned for this peak volume. This is where the pod restarts become visible. The increased latency triggered health checks to fail, which the platform tracks in real time. Without this unified view, you're left guessing if the pod restarts caused the latency or if the network lag caused the restarts. Finally, we see the resolution at T+38 minutes, when the interface was restored. The entire incident lifecycle is now mapped and indisputable. This factual baseline is what allows your engineering team to stop debating what happened and start fixing the structural weakness. One technical prerequisite for multi-source postmortems is timestamp alignment. Accuracy is everything. When events from 6 data sources are placed on a shared timeline, the accuracy determines whether the causal sequence is correct. A router whose clock has drifted 45 seconds from NTP will appear to have thrown errors 45 seconds later than it actually did. Monitoring platforms that normalize timestamps at ingestion, converting all sources to a consistent reference, eliminate this error class entirely. Data-driven postmortems also help distinguish correlation from causation. Many events happen in close proximity. It's tempting to draw causal arrows between them based on proximity alone, but that leads to the wrong conclusions. The full multi-source timeline reveals that independent responses often share a common upstream cause that occurred before the first symptom. The 5 whys process applied to real telemetry produces different answers than the same process applied to human recollections. The organizational value of a data-backed postmortem is in the specific action items it generates for the team. When the timeline shows a failover to an undersized backup link, the action item is specific. Resize the link now. When the postmortem is written from memory, the action item is often vague, like improve monitoring. Vague items get deprioritized. The quality of the postmortem determines whether the incident happens again. Data-backed analysis ensures it won't. The evaluation question. Starting from an alert that fired last Tuesday, can your platform show you a unified timeline? Can it show events from the preceding 10 minutes to the following hour across synthetic, SNMP, Flow, OTel, and Kubernetes? If yes, the postmortem is a data exercise. If no, it's a memory exercise. And memory is the least reliable source you have.